does work. Okay, cool. We're going to go and get started. So thanks everyone for being here today. Thanks to the folks online. And I know some people are still filtering in, but we'll try to stay on time. So really happy today to have Sam Crossley, who is going to be our speaker today. But I just wanted to give you a bit of background on Sam, who is now at LPL. So if you haven't seen him, he's here, second floor. What's your office number? 249. In case you're interested. So that's by the back door. So as you're going out, feel free to stop and talk to Sam every day. So Sam got his bachelor's degree from Hardin Simmons in 2010, and then joined the Peace Corps after that. Then came back to academia and got his master's at Texas Christian in 2016, and then started a PhD at the University of Maryland with Jessica Sunshine. Completed his PhD in 2021. In the midst of the pandemic. So good job to you for finishing during the pandemic. And then went to NASA JSC/LPI to do a named fellowship, the McKay Fellowship, and was there for 3 years doing his postdoc, and finished up in the fall of 2023, and then joined LPL in January of this year. And so today, Sam is going to talk about oxidized planetary differentiation. So where you go. Thank you. Let's give a round of applause to Sam.
Everybody hear me through the microphone back there? Take that as a yes. All right. Well, thanks for that introduction, Jess, and thanks everybody for being here. It's been a real pleasure getting to meet so many of you today, and looking forward to getting to meet the rest of you and strike up potential collaborations here at LPL. But before we get into this talk on oxidized planetary differentiation today, I just want to acknowledge collaborators, both past and present, some of which are actually here in the room with us. With working through all of these amazing people, I've gotten to learn so much, both through graduate school and during my postdoc. And it's really through assembling these incredible teams together that we can really accomplish novel science together. And so I just want to attribute proper credit to them. But now enough about them. We're going to talk about us now today. So in this colloquium talk, I'm going to provide some generous background in here, because I know that we have a breadth of different expertise and different topics here. So after we give sufficient background, we're going to start talking about what sample science can tell us about how planetary differentiation occurs in an oxidized setting and what that means, as it's informed by meteorite studies, through melting experiments with meteorites and mineral analogs, and through the trace element geochemistry that's ultimately preserved in these materials. And then once we've covered that topic, we're then going to turn our attention out into the asteroid belt and look for materials that may be consistent with these products of oxidized differentiation, both that we see in the meteorite record and through these experiments. So if you're maybe more of a visual learner like me, at the top right here, we have a nice thin section of a meteorite. So we're going to talk about the natural rocks that we can examine to learn about the early solar system, and then simulate these processes of how they actually melt and differentiate, and then ultimately look for evidence of this in the asteroid belt, and wrap up with a nice synthesis of all this at the end. So I imagine this is probably a familiar concept to most of you, but just to make sure that we're all starting off on the same page, when we're talking about a differentiated planetary body, we're talking about something that has melted and segregated out into these different components of a silicate crust and mantle and a dense metallic core. How ultimately do we achieve this structure in a planetary body? We don't start out this way. These materials don't just accrete into these stratified structures. And the sequence of differentiation actually can diverge according to the materials that they originally accrete from, and ultimately through the thermodynamic properties of these different minerals that they're composed of. So there are a couple of different schools of thought on how you go from these initially accreted materials to these evolved structures. One is through sequential partial melting, where you first form a metallic core, followed by the melting and segregation of a silicate crust, and leaving behind this residual silicate mantle, and that's pictured by this diagram at the top right. Alternatively, and particularly for much larger planetary bodies, it's thought that planetary differentiation occurs through extensive or complete melting, and through this magma ocean scenario, as it's often called. You rain out these dense materials that ultimately go to the center of the body to form the core, and through crystallization and flotation, of silicate phases, you ultimately form the crust and the mantle. And whether or not we go through this sequential process or whether it's through extensive melting or a combination of both ultimately depends upon a number of different factors, such as the composition of these core-forming melts that may ultimately sequester to the center of the body, the composition of unmelted silicate phases and when they will melt. The geometry of those grains can ultimately pinch off some of these melts and prevent them from migrating until extensive enough melting occurs. And the volumetric proportion of the melt relative to these unmelted phases can determine whether or not they can connect together and migrate in mass or not at a given pressure or temperature. And for the purposes of this talk, I want to highlight these first two components. These are generally thought to be the primary controls of whether or not we differentiate through this sequential manner or through extensive melting, which are the composition of the core-forming melts and the phases. And these are actually functions of where these materials ultimately form in the early solar system. So in a very simplified model, the distribution of chemical environments in the early solar system, it's generally thought that the oxidation state increases as you move away from the sun, basically due to the precipitation of more volatile phases like water ices and other things like that. And as you actually come into the side of the snow line, which isn't generally pictured here, but let's say, for example, that you have a snow line occurring where this material is gathering here, you actually still have an oxidation gradient there as these materials inflow from the outer solar system and evaporate and oxidize and sulfidize or whatever volatile phase may be occurring there, those materials that are inward of the snow line. So as a consequence, the materials that form in these different regions of the solar system are going to inherit different mineralogies as a function of these different oxidation states in their nebular environments. And these different mineral assemblages are ultimately going to undergo different geologic processes because different minerals have different physical and chemical properties that they will experience at a given pressure and temperature. So this process of early differentiation where we are accreting materials and they undergo solid state alteration and ultimately melting and sequestering to form the crust, mantle, and the core are actually sampled through the natural laboratory. We're provided through meteorites. These are provided through things like chondrites, primitive achondrites that sample these various stages of planetary differentiation. So to understand how planetary differentiation occurs as it is informed by these meteorites, we need to consider what each one of these groups can actually tell us about not only how differentiation occurs, but how it diverges according to the chemical characteristics that they inherit from their environment. So we'll start by looking at chondrites. These are materials that have accreted from the protoplanetary disk that have otherwise undergone limited alteration on their parent body. They may have undergone some solid state thermal alteration or metamorphism. They may have undergone mineral and fluid reactions on their parent body, but have otherwise unmelted. And so they provide us some valuable information about the different chemical environments of the disk from which they come from. But if we want to understand how these different materials melt and differentiate, that requires us to simulate that process, either through actually melting the materials or through analogs of these materials, or through numerical modeling to understand how these materials ultimately differentiate to form that stratified structure. On the other end of the meteorite spectrum, we have the achondrite meteorites, which represent various components of these fully differentiated or partially differentiated bodies. So we may have materials from the crust or the mantle or the core of a parent body, but they don't necessarily provide us a complete record of the bulk parent body. And it's notable that we don't actually sample all of these components for any one parent body. So we don't ever necessarily have a full picture of the products of planetary differentiation from a singular parent body. So those nebular characteristics that we're interested in, like the oxidation state in which these materials form, may be overprinted by these processes of melting and other processes that are occurring within the parent body. So we can learn about the products of differentiation, but not necessarily how they result from the environments in which they form. But there's a nice sweet spot in the middle where we can take a look at these primitive achondrites, which are partially melted materials that are arrested in various states of differentiation. So they've melted from degrees of something like 1% of the mass of the material up to 30% of the mass of the material. And because they've experienced these high temperatures for prolonged periods of time, their mineral chemistries and their textures are equilibrated. So we can use things like thermodynamics to help predict what will happen with continued melting or how they reach this point. And in particular, by comparing them to chondritic mineralogies and chemistries, we can make predictions about what materials have been lost and how differentiation begins to occur with these materials. So they really offer us unique insights into this process of differentiation and how it begins in planetary bodies. And in particular, if we're interested in how oxidation and things like the sulfur content of materials ultimately affect how they differentiate, the primitive achondrites record a wide range of oxidation states over 3 orders of magnitude in oxygen fugacity, which is how we measure the oxidation state of rocky materials. And these are sampled by 3 different broad groups of primitive achondrites here. And as a result of these different oxidation states, the main effect that you'll see with this is that ultimately it changes the mineralogies within them, primarily by controlling the average valence state of transition metals like iron, which is the most abundant of these transition metals in planetary materials. So in the most reduced of the primitive achondrites, most of your iron is going to exist in its native metallic form, and you're going to have lots and lots of metallic iron in these materials. And as you progressively oxidize them, the native metal will convert into ferrous iron. So that iron will partition into silicate phases. You'll end up enriching all of your silicates in iron. And then as you progress to even more oxidized conditions, you may get ferric iron, and some of that iron is going to start partitioning into oxide phases. So this wide range of oxidation state is ultimately manifested in the mineralogies of the different primitive achondrites. And because we're interested today in talking about how oxidized differentiation is going to deviate from these more metal-rich materials, we're going to focus in now a little bit on the Bratchenite meteorites, which actually still record quite a wide range of oxidation states. This represents about 1 to 2 orders of magnitude difference in oxidation states between the most reduced and the most oxidized Bratchenites. So that's going to affect not only the mineral chemistry of these materials, but actually the modal mineralogy, or the abundance of the different mineralogies that we see within them. And so for our oxidized in-member Bratchenite here on the left, sample name is NWA 4882. And this is a false colored classification map. So the different minerals are colored according to the legend down here at the bottom. You can see that the oxidized Bratchenites are dominated by the silicate mineral olivine with lesser amounts of high calcium pyroxene and chromite. And the core forming minerals within those are pretty much exclusively iron sulfides. And you can contrast that to the reduced Bratchenites over on the right. You see that there's much more diversity in the silicate mineral assemblage. You have core forming mineral assemblages that are composed of both iron sulfide and iron nickel metals within them. And this is again a function of the differing oxidation states between them. Just to summarize the kind of difference that we're seeing between these two, the more oxidized materials are going to generally be more rich in this ferrous iron. They're more rich in the olivine silicates as compared to the reduced materials, which have a greater degree of the pyroxenes and other phases within them. But interestingly, geochemical modeling for these materials suggests that they've undergone similar degrees of melting and similar degrees of melt loss. So this difference in mineralogy is not something we can attribute to how much melt was lost from the system, but is instead a function of the different oxidation states within them. So what does that ultimately tell us about the differentiation as a function of oxidation state? How is this process going to diverge as recorded by the Bratchenite clan meteorites? So if we assume a chondritic starting composition for these materials, we can start to piece together the missing components by looking at the oxidized versus the reduced Bratchenites and see what the crustal components and the mantle and the core components should look like for these undifferentiated materials, and what they would look like if we can actually sample all of these individual components. So for the oxidized Bratchenites, their crust is going to be more rich in plagioclase with minor amounts of olivine and pyroxene. Compare that to the reduced materials, which you would have more typical basaltic compositions among planetary materials, which is really a 1-to-1 ratio of plagioclase and pyroxene. The mantle, again, is going to reflect these sort of Bratchenite mineralogies. It's going to be generally more enriched in olivine and overall more rich in the ferrous iron, with reduced materials having more pyroxene within them. But the core is really where this starts to get a little bit more interesting, because the geochemical modeling suggests that to reproduce something like a chondrite from these assemblages, we must have lost some degree of iron nickel metals plus sulfides. But really, these geochemical models are sort of confounded by what we see in the Bratchenites. And to illustrate this, what we can do is start to look at the trace element compositions within these materials. And trace elements, if you're familiar, are present in parts per million, parts per billion levels. And because they are present in such small quantities, they behave very predictably during geologic processes. So we're going to take a look at the noble trace elements. These are also called the platinum group elements: rhenium, osmium, iridium, ruthenium, platinum, and palladium, everybody's favorite trace elements. And what we're going to look here on the y-axis is just concentration normalized towards CI, which is generally used to approximate bulk solar system compositions. and we've ordered them here in their decreasing compatibilities with metals. And for the reduced brachyonite metals, they come in pretty typical patterns, and this pattern here is consistent with loss of a small amount of sulfur-rich metals. And you can see that if we compare the concentrations of these noble metals with the sulfides, between the metals and the sulfides, that the metals are enriched by several orders of magnitude. This is pretty typical noble metal behavior in planetary materials. The oxidized brachyonites, however, contain them exclusively within the sulfides. And not only that, but they contain them in proportions that we really can't reproduce at all through partial melting of metals. In particular, these depletions in iridium and platinum relative to the other noble metals are not something that are easy to explain through partial melting of metals. So this was something that we noticed in the work that I was doing during my dissertation. And so we thought, well, okay, if we can't explain this through partial melting of metals, then what can we look to actually reproduce these anomalous trace element signatures? And so we turned again to the chondrites to see, are there materials that could represent the precursors of the oxidized brachyonites that might explain these anomalous trace elements? So for that, we turned to the most oxidized and sulfur-rich materials from the inner solar system. These are the Rumerudi or R-type chondrites. They are so oxidized that they lack iron nickel metal in any appreciable quantities. They're only there in trace amounts. Even then, they're very, very nickel-rich in that case. But they do contain multiple species of iron nickel sulfides, specifically pentlandite, which has about equal proportions of iron and nickel, and pyrrhotite, which is a nickel poor sulfide. And what we found is that these anomalous trace element ratios can actually be reproduced or are reproduced through the R chondrite pyrrhotites. But that actually the primary holder of most of these noble metals are pentlandite sulfides. And so what we proposed was that perhaps we can form these brachyonite, oxidized brachyonite sulfides through partial melting and segregation of a pentlandite liquid, leaving behind this brachyonite iron sulfide residue. And this actually carries a really interesting implication for the process of differentiation if this is indeed what happened. So if you're unfamiliar with these ternary diagrams, you just need to know that as close as you get to the vertices of these diagrams, the more enriched you are in that given element, iron, nickel, and sulfur here. So I've plotted up the bulk metal and sulfide assemblages of some of the more reduced chondrites. These are the ordinary chondrites for those who are familiar with meteorite terminology. Those are in the blues and greens down here. They fall within a stability field for various metals and sulfides. So down here, the metals, chemosite and taenite, and the iron sulfide pyrrhotite. So all of their core forming minerals are going to be composed of those three phases. Whereas the R chondrites are composed, they fall in this stability field here just for pentlandite and pyrrhotite. Now, as you start to partially melt these materials, let's say we increase the temperature up to the cotectic where metals and sulfides will both start to melt. You can see that the composition, which are represented by these dots here, of the melts for each one of these phases actually differ not only in their iron and nickel content, but also in their sulfur content. And what's interesting about this is that the composition of the melt for the R chondrites actually may have physical properties that make them capable of percolating between silicate grains prior to melting of any of the silicate phases. Whereas the metallic melts produced by things like the ordinary chondrites have much higher viscosities, much higher surface tensions, and require silicate melting to provide them a migratory pathway to ultimately migrate. So taking us back to this idea that different regions of the solar system are ultimately going to influence the mineralogies of these materials, and these mineralogies ultimately follow different evolutionary pathways, this led us to propose this general idea that there's a divergence of core formation pathways as a function of things like the oxygen fugacity of the system, where more reduced systems are going to be dominated more so by iron metals in their core forming components, and so they're prohibited from this percolative mechanism for core formation, in contrast to the oxidized materials that may, according to some studies, at this point in the talk anyway, may be capable of wetting these grain boundaries and migrating to ultimately form a core at lower temperatures and earlier in the sequence of planetary differentiation. And this is where I took some of these outstanding questions and moved down to Houston to do a postdoc to address these questions really more directly, because we really only had indirect evidence for whether this process might occur or not at this point in the study. And so what I wanted to do is address these questions, which are, can we actually percolate these sulfide melts through an otherwise unmelted oxidized chondrite assemblage? Remember from the beginning of the talk, we listed this whole thing about all these different factors that we need to meet to be able to percolate these melts through materials that had never really been addressed with actual meteorite materials before. So we were always kind of just missing the mark in terms of the experimental parameters that we needed to assess whether it can happen or not. And if it can happen, what kind of geochemical evidence can we look for that we can definitively say this actually did happen in the early solar system? What can we look for in meteorites that would actually tell us whether we fractionated these sulfide melts to form a core? So for the first part of this question, to address the question of whether these melts can percolate or not, we did a series of partial melting experiments to see if we can actually make these sulfide melts percolate prior to silicate melting. For this, we used one of these highly oxidized and sulfur-rich R chondrites. This is an equilibrated mineral texture for the specific sample. So we think it's representative of the textures and the chemistries that you would expect for materials just at the onset of the melting of these sulfides and at the onset of melt percolation, if it does happen. We subjected these to from temperatures from 900 to 1,000 degrees centigrade, which isolates the melting of the mineral pentlandite and its reactions with residual pyrrhotite. So no melting of the silicates within those. And before and after each one of these experiments, we scanned these with micro XCT, which you're seeing are unmelted samples spinning around over on the right side of the screen here. And in doing so, we can observe any changes in morphology and migration of these sulfide melts throughout this temperature range. So just to show you some of the largest sulfide components before heating here, I've just colored them according to their volumes. And we're actually kind of surprised to see these already extant sulfide assemblages within these. These may have been produced through impact melting of the sample. Chondrites, although unmelted in terms of the parent body, have undergone rather complex histories prior to that. So they may have melted and formed these networks through impact melting or hydrothermal alteration. But after we've subjected this material to heating at 1,020 degrees centigrade, you can see that the largest sulfide melt networks have changed in their locations. Some of the large materials, like the ones up here that you saw before, have been severed into smaller melt networks. We formed completely new melt networks over here. So there seems to be redistribution of these sulfides by 1,020 degrees centigrade due to melt percolation without any invoking of silicate melting. But just to be sure, we wanted to take a higher resolution scan of this and see what really is the mechanism for this redistribution of sulfides. So we excised a small subvolume of this and analyzed it at the University of Texas Computed Tomography Lab. You can see the full subvolume here. It's about 700 microns along its longest axis. I've rendered the silicates semi-transparent, and the sulfides are in white here. They're the most X-ray attenuating phase, so they're going to show up the best in these scans. And just to show you the formation of these really nice complex web of dendritic and vermicular, so I'm using geology terms, this really nice web of different melt veinlets that are connecting all of these different reservoirs together. And you can actually see the formation of these little vesicles, these little bubbles that form as these melts drain out from their melt reservoirs into the surrounding silicate matrix. So we do seem to be able to percolate these melts prior to silicate melting in these chondrite assemblages. So what we want to do next is see, is there any geochemical evidence that we can use that's consistent with this process to identify whether this actually happened in meteorites like the oxidized brachynites. And so for that, we're going to turn back to our noble metals that we were talking about earlier. And remember, we made this observation that in the reduced materials, they're going to partition very strongly into metals. So not only that, but they have a particular compatibility sequence with osmium, iridium, and ruthenium being more strongly compatible with these metals, sometimes platinum as well, depending upon the sulfur content of the melt, but palladium is going to be incompatible with them. We contrast that to their abundances in these sulfides. You can see that they have a different compatibility pattern, with osmium and ruthenium still being compatible, iridium less so, and then both platinum and palladium being incompatible to different degrees in these residual sulfides that we would expect to be left over after partial melting. So because of these different compatibilities, we would expect there to be distinct fractionation between these two systems during melting of sulfides versus melting of metals. And we expect that, but the truth was we didn't actually have partition coefficients that we needed to model this at the time. There are lots of studies out there from economic ore studies looking at how sulfides partial melt. These are very valuable materials, but don't necessarily reflect what we see in the R chondrites. So we had to make our own. So what we did is we synthesized the pentlandite and troilite or pyrrhotite in these chondrites. We doped them with trace metals to 5 parts per million and subjected them to the same temperature range that we did for our melt percolation experiments. And in doing so, we can compare the interelement ratios of these residual sulfides that you can see over here on the right with the compositions that we see in the oxidized brachynites and see, can we actually reproduce what we see in the brachynites through percolative melting of these sulfides. And so again, we have concentrations here on the y-axis. These are all going to be normalized to iridium because we're looking at interelement ratios, not necessarily concentrations here. And they're ordered in their compatibilities with the iron nickel sulfides. And what you see in the gray here is the full range of different oxidized brachynites and related basaltic melts, the full range of the different noble metal interelement ratios. So from the results of our 1020 degree experiments, which again is where we saw this percolation occurring, you can see that we yield the right compatibility sequence of these elements, but it's too strongly fractionated. This is actually a good problem to have because through continued batch melting, we can see that through extensive melting of these different sulfides, we can reproduce the full range of noble metal ratios, both in the oxidized brachynites and very importantly, in those related basaltic components. And this is a point I really want to emphasize here because in order to reproduce this pattern in both the restites, the residual unmelted brachynites material, and in the crustal melt material, we must have lost a sulfide melt component prior to the melting of silicates. Otherwise, these incompatible elements, palladium and platinum, and to some extent iridium, would be enriched in the crustal component. So the fact that we have these incompatible depletions in both the crust and the mantles of these materials points to the idea that we must have fractionated these sulfide melts prior to silicate melting. And the most reasonable interpretation for that is that these materials have sequestered according to their higher densities, ultimately to form a core within similar planetary bodies. So I also want to point out that this is a really interesting consequence. The products of these different pentlandite-rich melts that we produce are not necessarily going to crystallize as pentlandite, because these sulfide minerals are actually melting in a peritectic reaction. We're influencing the composition of the residual minerals. So we're actually changing the composition of the melt and the residual materials as these systems are melting. And as a consequence, this composition of the liquid melts that are produced through partial melting of these sulfide systems actually crystallize within this stability field here, which includes both a number of different sulfides that can crystallize, but also nickel-rich iron metals. And so this is actually something that can go a long way to explaining why we don't actually see any of the sulfide-dominated meteorites that we might expect if they do indeed form cores. Sulfides are actually quite brittle. They're probably not going to survive things like atmospheric entry and weathering and impact processes, but they will, or they can crystallize a nickel-rich metal fraction from those liquids. And we do actually sample these among some nickel-rich ungrouped iron meteorites. And this is something that we're investigating further now to see if the trace element compositions of things like Octabeha County, which is 60 atom% nickel. It's basically not an iron meteorite, it's a nickel meteorite at that point, I guess. We're going to see if the trace element patterns of that actually align with this process of crystallization from a sulfide melt. So that's something that we're currently investigating. Now, just kind of as a general observation, most of the bulk products that will crystallize from these pentlandite-rich melts are going to have iron-nickel ratios that are less than 1. So that's interesting because it's something that we can actually resolve with something like the onboard gamma-ray neutron spectrometer for Psyche, which I know would be a pretty wild explanation for what Psyche is, but it would go a long way to explaining the density deficit for Psyche if you do want to invokes that it may be some type of core. The density for iron nickel metals are about double at least of what we see, or what we've calculated for the density of Psyche. The density of iron nickel sulfides are much closer to that. So potentially, if you're going to invoke mechanisms like ferrovolcanism and all sorts of cool, wild stuff, then hey, why not consider that perhaps Psyche could at least have much of its composition contributed through sequestration of these sulfide melts. Perhaps more relevant to that is the very large fluid and presumably sulfur-rich core of Mars, which I know some of you are quite familiar with these results. There's been a lot of backbreaking work trying to figure out how we can accommodate such a large fluid core in the interior of Mars, because it seems to be at odds with some of the geochemical data we have, particularly for these noble metals and the loss of presumably metal-rich fluids. But I would propose that under these circumstances, especially considering that Mars's oxidation state during core formation is actually pretty close to what we've measured for the brachinites, it's possible that we have a much greater contribution of sulfides to the formation of the Martian core than we otherwise had thought. So that's also something that we're looking into. So hey, maybe next colloquium we'll have some good answers for you on that one. But just food for thought now. So I want to take a moment now. We're going to shift focus from our meteorites and from our experiments to looking at what the asteroid record can tell us. And so I just, in doing so, want to acknowledge that there are some biases, certainly, in trying to interpret these planet formational processes from meteorites. They are not a complete record of solar system materials. We know that just because most of the meteorites that we have are not necessarily reflected in many of the remote sensing characteristics among asteroids. The meteorites that we do have are filtered, as I mentioned earlier, perhaps as an explanation for the lack of sulfide meteorites. They're filtered through impact and atmospheric entry, so we only sampled the stuff that can survive that in the first place. Also, not to mention terrestrial weathering, which sulfides also really don't like. And we also may be temporally biased. I mean, necessarily the meteoritic record that we have today may not be reflective of the materials that we're accreting to the early Earth, and certainly aren't representative of the solar system as a whole. We can gain additional insight into this by taking a look at asteroid populations as informed by coordinated meteorite investigation. So we can use tools that we can apply to both meteorites and asteroids to provide us a better picture. And in the context of this talk, understand how things like the population of oxidized materials are represented among asteroids and how that compares to more reduced assemblages. They're quite rare among the meteorite record, but that may not necessarily be true among asteroids. Can we utilize any characteristics of meteorites to remotely interpret their oxidation state and their petrologic history? But to do that, we need a tool set that we can apply to both of them. So for us, what we chose to use for that is reflectance spectroscopy. So some of you I know are more astronomically oriented and may be familiar with this stuff. But just in general, what we're looking at is a log scale of the reflectance of material across the wavelength from the visual to the near infrared region of the electromagnetic spectrum. And this background reflectance or continuum is essentially what the light would look like if we had no absorption features within them. But minerals produce these distinctive absorption features. This is olivine here, centered around the 1 micron region. And we can use these to remotely interpret what minerals that are at least spectrally active in the visual to near infrared range are present in an asteroid. These are generally composed of overlapping absorption bands. So in order to adequately interpret their composition and what petrologic histories they may be consistent with, we need to deconvolve these different overlapping bands ultimately. So not only that we can interpret these different aspects of it, but so that we essentially have some way to test for self-consistency within model solutions. So the way that we choose to do that is through modified Gaussian deconvolutions. We basically take these overlapping features, and each one of these absorption features are produced by ferrous iron in octahedral coordination sites within silicate minerals. And the different band parameters, like the amplitude and the center of these different bands, are going to vary depending on how much of this ferrous iron is present in that silicate mineral. And so what we do in these models is we use inverse and stochastic fitting functions. So we just change the width or the amplitude or the position randomly of each one of these figures. We assess whether the residual error is improved relative to the actual data that we've measured, which is here in red. And essentially we do that until we can no longer improve the residual error greater than the actual measured uncertainty of the asteroid. And in doing so, we can assess whether each one of these individual bands produce self-consistent results for how much ferrous iron there should be in the silicate phase. So we tested this both with our meteorites. So this would be an oxidized brachyonite, which is composed, again, remember, primarily of iron-rich olivine. And you can see over here our reduced materials. They also produce these pyroxene absorption bands at 1 and 2 microns. But our approach in doing this allows us to fairly accurately measure the composition of both olivine and pyroxene in these cases within about 10 mol%, which is what is realistic generally for these remote sensing, particularly of asteroids, when you're going to have even larger uncertainties on your asteroids, larger uncertainties on your measurements, sorry. So we were able to successfully deconvolve these and get their compositions. And if we apply these to the different asteroids that you can see, like so for asteroid 354 Eleonora, which is actually like 80% of the mass of all of these olivine asteroids. It's like most of the olivine in the asteroid belt. We can fairly accurately reproduce, or with some confidence, we can reproduce the iron content. Sorry, this is phaolite content, which is just shorthand for the iron content within olivine, and ferrocylite is the iron content within pyroxene. So we're able to do this in a self-consistent manner, fitting these band sitters, estimating their strength ratios, so the ratios of pyroxene and olivine, to get an idea of how much pyroxene and olivine there are in there relative to each other. And we can use this to make some interpretations of what they would be consistent with in terms of a petrologic history. So just looking at something like this is a pseudo phase diagram looking at olivine ferrous iron content, and these dotted lines represent the proportion of pyroxene relative to olivine. So 10% of the high calcium or low calcium pyroxene in blue, for example, would fall along this blue line here. And for all of our olivine dominated asteroids that we're looking at for evidence of these oxidized materials, we're basically looking at materials that fall to the left of the phase of this pink line in the phase diagram here. And so what we can do is we can use the information interpreted from the iron content of these different silicate phases, along with the proportions of olivine and pyroxene, to plot where they would fall in these phase diagrams. We can make some estimates about the temperatures that they reached and what melting events they may have experienced, whether they're chondritic, whether they're achondritic. Yeah, we can actually track things like, yeah, we're going to like move up in this direction essentially and start to partially melt these materials. So in applying this to, there are about, I think, 20 A-type, which are the olivine dominated asteroids that we could get complete data sets for. These are actually quite rare materials in the asteroid belt. As you can see, all these other dots represent other asteroids. So they're quite rare. But even among these, they are almost entirely dominated by these oxidized olivine-rich assemblages. At least two of those, 354 Eleonora, and I think this is Eternatus, which I think is 446 Eternatus. Two of these are large enough to possibly have experienced core formation, at least according to dynamical models. But there's really not any significant amount of reduced olivines among them, which is interesting. You know, we would expect there to be quite a bit of those. If we look at the meteoritic record, most of the intersolar system stuff is comparatively reduced. We have quite a few basalts, but we don't seem to have the corresponding mantles to them. So why is it that we have this bias towards the oxidized and olivine-rich materials among the A-type asteroids? Oh yeah, and I forgot to mention, we also have these really weird things in blue here. These are materials that have ferrous iron content that are in excess of any materials that we actually represent in the meteoritic record. It's something like 60 mole% ferrous iron within them. Remember, our most oxidized brachinites were like 30 to 35. So twice as oxidized, if that is the factor for it, twice as ferrous iron rich at least as the brachinites. So what are those? Sorry, spoiler alert. Well, so they're consistent with these high ferrous iron contents. Well, one of the first thoughts that we had was maybe we're just overestimating the ferrous iron content of this. MGM can do that, but it's generally something like 5 mole%. So probably not that from our model fitting. There is evidence that shows that space weathering can push these band centers to longer wavelengths, which would correspond to more ferrous, or which would at least be interpreted as more ferrous iron-rich olivine. But that doesn't really seem to fully account for how iron-rich these materials are. So if you do want to believe that these materials really are so ferrous, there are a couple of different explanations that might work. One is that they might have been initially aqueously altered. This can increase the ferrous iron content of the silicates, although in that case you would then have to dehydrate them because we don't actually see any evidence for hydrated phases like phyllosilicates within the spectra of these materials. Another possible explanation is that they are just really matrix rich. We do have matrix phases within, say, the archondrites that reach these high ferrous iron contents. So one potential explanation from that is that you've partially evaporated and then recondensed chondritic materials. So you're preferentially forming these matrix rich, really ferrous iron rich materials. In that case, they're not necessarily high oxidation state, but this is still an outstanding question from that work. What are these really ferrous iron rich materials? Maybe some of you guys have thoughts on that. But we think that they must have been, if they are really this ferrous, they must have been primitive assemblages because phthalate of that high iron content, it's just not stable at higher temperatures where you're starting to partially melt materials. So we think that they must be relatively primitive assemblages. Now to that question of where are these reduced mantles, I think the truth of this is that we're looking in the wrong place for them. So these reduced bodies, as we noticed back with the brachynites earlier, the more reduced materials have much lower olivine pyroxene ratios. So there's a greater abundance of pyroxene in them to begin with. So if you wanted to start with something like an ordinary chondrite and partially melt it to the extent that it is dominated by olivine and would fall within this classification of olivine dominated asteroids, you'd have to partially melt it at least 30%. And you would have to, reach that temperature and sustain it for long enough in order to sequester these materials, which would require a large body. And so at that point, how do you isolate this olivine at the surface of a material so that we can actually measure it with remote sensing without completely disrupting the body? So I think ultimately these reduced materials are probably just accounted for among other asteroid classes, ones that have greater proportions of pyroxene. Maybe something like the S-type asteroids are better places to look for the reduced mantle materials. Also, if they have higher metal contents within them, remember these reduced materials not only differ in their silicate mineralogies, but also in their core-forming mineralogies. If they have higher metal contents within them, and it hasn't been efficiently able to sequester down to form a core, that can distort your spectra, obscure your olivine bands. And so perhaps we're, again, not just looking in the right place. We need to look for things that have less diagnostic olivine signatures within them, both for the metal and the pyroxene content. So ultimately, really, these olivine-dominated asteroids are just biased towards these ferrous iron contents by definition. So not necessarily that all of the olivine-rich asteroids in the main belt are oxidized or ferrous iron-rich, but just that we're looking at a very narrow subset that by definition are going to only include these oxidized materials. So just to synthesize some of this material together, this oxidized and sulfur-rich differentiation occurs along a different evolutionary pathway from their reduced counterparts. It yields a more felsic, in the case of the brachynites, a more plagioclase-rich crust, more Ferroan olivine-rich mantle, and ultimately can sequester to form a sulfide-dominated core. This is evident in the geochemistry of primitive oxidized achondrites, the brachynites. And then most of these olivine-dominated asteroids are ferrous iron-rich. Some of them may have formed sulfide-dominated cores. Oxidized chondrites are also possibly included among these materials with matrix-rich assemblages. And the reduced olivine asteroids are probably accompanied by significant quantities of pyroxene. So if you want to look for these missing mantle components that are often talked about and try to search for the different differentiated components represented among asteroids, maybe we should just be looking elsewhere for them, possibly among the S-type asteroids. So yeah, I'll be happy to take any questions. Thanks for your attention.
Any questions for Sam? Oh.
This might be like too hypothetical, but if you had a or if we consider, I guess, in the figure kind of the crest of that, like maybe something that things are differentiating, what do you think that would look like?
Like it didn't heat up to the point that crust, is that what you're asking?
Or rather, if we had like a parent body and it's getting hot and forming a core, if the brachynites are thing, or if there's sulfide melting and you see those sulfide assemblages and melts and whatnot, are there anything that was cooler and maybe less heated that was like, do you have any
that might have been like
as to like what that
frozen in that state of just where the sulfides have segregated, or
I guess prior to sulfide segregation?
Oh, prior to that, well, prior to that, you would probably just have something that would look more like a chondrite assemblage, right? So it might. So this is an interesting question when we're talking about the precursors of some of these differentiated materials. People often will talk about, maybe it's like an ordinary chondrite, maybe it's like an archondrite. I mean, the truth is that we don't actually sample the precursors of those materials because they became these more evolved materials. For the brachynites, we'll look at the ordinary chondrites or the R chondrites that serve as analogs of the different oxidized and reduced end members. Although I think for a number of them, they probably are something in between. It may be that there was some metal present in the brachynites, but that they're dominated by sulfides. There is a stability field in iron, nickel, sulfur space where you can have coexisting pentlandite, pyrrhotite, and these different metal phases within them. And that's possible that that's really what the brachynites represent. But if you were looking at this in terms of what would that look like in a remote sensing aspect, like what would we look for that? It would probably look more like one of these chondritic assemblages where you have ferrous iron rich olivine and some small component of pyroxene within that as well. Yeah, that's what I would guess. Yeah, thank you. Yeah.
Any other questions in the room? Okay, I'm going to give it to Scott and then I'll check the Zoom.
You showed that these sulfur-rich oxidized meteorites can form these percolative networks. Is it possible to speculate or model if these bodies can form a core earlier, like how long that process would take compared to completely melting for the more reduced ones?
Yeah, so
separated metal core.
I was having an interesting conversation about this with Carmen Dumocha earlier. He does a lot of physical properties of rheology of magmas and things like that. And so we were actually talking about, the general assumption is that over some period of time on these small bodies, that you do ultimately segregate these materials according to their density. Although I think there's sort of an outstanding question of, with such a small body, is the gravity in them enough to actually segregate these materials out according to density? So to kind of answer your question, I would say it depends on the size of the body, what the size of that, or what the timing of that's going to be, because I think the influence of gravity versus, say, the interfacial tension between the sulfide melts and silicates, you're going to have to balance those forces in terms of, are they propagating out according to the interfacial tension? Are they propagating downward according to gravity? So I think it's going to vary depending upon parent body size.
Okay.
That's my speculation on that. I think
So
there's
if
a
you
lot
could-
more work to be done.
If you could ignore gravity,
Ooh,
would-
okay, yeah, I'm good at that. Yeah.
so would these sulfur oxygen rich bodies be able to form a core as a smaller body if they can melt and percolate at a lower temperature?
The percolation that we observed in these experiments, occurs over a day. So the speed at which these melts actually move through the material presumably could happen fast enough. We haven't done the calculations to say what's the melt flow velocity of these. I think that's the next step for these 3D models, is to take it to some mineral physics folks and say, like, what can we actually calculate the permeability of these melts to be? What would the melt flow velocity be under a given condition? And does this happen fast enough to essentially beat the increasing temperatures, at which point, you're going to hit the eutectic or sulfide melting. And at that point, these sulfide melts are so viscous that any sulfide melt, silicate melts, sorry, are so viscous that any sulfide melts are going to get entrapped within them during melting of silicate. So it is sort of a race against the clock, I think, but I don't think that we have a good answer for that yet. Yeah.
Any other questions in the room? Oh, Bo, again.
Sorry for two questions. This might be a dumb one, but do you need an already oxidized precursor material to form something like a brachytite?
Or to form the oxidized brachytite, certainly. And okay, so I guess I should take a step back and say that when I use terms like oxidized and reduced, like, these are relative terms, right? So these are oxidized for meteorites. So if there are any terrestrial geologists in the room, they would be laughing when we call these oxidized, because they're many orders of magnitude less oxidized than things that we see at the surface of the Earth. But for meteorites, to get mineral assemblages like the brachynites, it does need to be an oxidized assemblage, unless you are inheriting really non-chondritic starting compositions for these materials. And as chondritic, we're using that in the loose term to mean sort of bulk solar system composition. So for these materials, you would have it. Now, you could also have a really high sulfur fecacity and sulfidize all of your metals in that way. But then we're starting to get into really sort of niche. We can talk about this later if you want, but I don't want to bore everyone else to death if I haven't already. of what oxygen fugacity actually means, because it's not like a real thing. It's a thermodynamic byproduct that we use to describe the electronegativity of these transition metals. And so, yes, necessarily by definition, we do have to have a high oxygen fugacity, but we're not saying that there is high oxygen content necessarily. It's just used as a proxy to describe the electronegativity of iron essentially in these systems. So yeah, good question.
Any other questions in the room? I know there's spectroscopists out there. There must be questions.
I think your student has one.
A non-spectroscopist is going to ask a question.
I guess, I don't know. Hopefully I'm not like, I'm still stuck on like the silicates of like the oxidized brachynites having less diverse silicate phases. Like, so then if you're having this sulfur rich differentiation, like what is that sulfidization telling you then about the partitioning and all of these silicates? Because I mean, coming from like Albright reduced world, like those on the very reduced end member, they have like no silicate diversity. So like what's happening here in the oxidized story, I guess?
So yeah, across this oxidation gradient, a general observation that you can make, and this is again specific to the oxidation range we're talking about, so you don't want to talk to like a terrestrial geologist about it. You don't want to talk to it anyway. But well, what you're really looking at here is for, let's say, olivine pyroxene ratio. The olivine pyroxene ratio of a material is going to increase with increasing oxidation state across the range of meteorites. So the diversity of these materials are going to be lower in the more oxidized materials because at the expense of pyroxene, you're forming more and more olivine in terms of the normative mineralogy within it. Now, for the other phases, like plagioclase, that aspect actually is related to melt extraction that's happening in these samples. So plagioclase is going to be like your first silicate phases that you're going to melt and fractionate in these. So that actually is a function of it. But for the other ferromagnesian silicates, like the olivine and pyroxene, that's a function of oxidation state.
I have a question based on this slide.
Okay.
So we don't have a good representation of the olivine bearing asteroids, right? There aren't that many of them. So you said maybe we go and look somewhere else and we might find them. We don't have many representations that we know of sulfide dominated cores.
Yep.
We also don't have, at least to my knowledge, a good idea of where the felsic crust is.
Yeah, we don't. And so for the I'm sorry.
No. Well, where are they? Like, did something happen to those bodies in particular that?
Yeah, so there are various ideas of what may have happened to these. So for the felsic crust, actually, we have a few samples of this in the meteorite record. We would love to get good reflectance spectroscopy data for them. Unfortunately, they're quite weathered, and it's really hard to actually get out this weathering without damaging the silicate phases that we want to look at, particularly because they're plagioclase dominated. Plagioclase has like a very weak 1 micron feature in the reflectance spectra. And if you damage the sample at all, you're pretty much going to lose that. So it wouldn't necessarily be representative of it. It may be that some of these felsic components are represented among, again, things like the S-type asteroids, but ones that are very, very ferrous iron rich. So perhaps some of them are represented among those anomalously iron-rich olivine materials that we noted, although the proportion of olivine and pyroxene in them isn't what we would expect them to be at equilibrium. But if these things have undergone subsequent impact histories and remixed together, that may not necessarily break that possible conclusion. For the mantles in general, one of the proposed ideas for why we lack so much of them, not only in the asteroid record, but in the meteorite record. I mean, the brachinites and things like that are quite rare, and they're not necessarily mantle materials that correspond to like all of the different crustal materials that we sample. One of the ideas is just that peridotite assemblages, like these things that are rich in olivine and pyroxene, are quite brittle, and so they just don't survive. And that's probably the case with sulfide-rich materials as well. And if we're actually not forming a core, as we were perhaps thinking about earlier, if we're actually still keeping all of these sulfide melts embedded throughout the mantle materials, that's just further going to weaken their mechanical strengths within them. So it may just be that we're just preferentially biased against them through impact even if they're out there, they might not make it intact to the Earth's surface very often. So
This sounds like a great problem for Robert. Building materials and bodies from brittle materials or breaking them apart.
oh yeah,
One of
we
our
can
grad
smash that.
students. So yeah, we'll get you in touch with him. Any further questions? I'm going to check if there's anything online. No questions online. So if there are no other questions in the room, going once, going twice, 3 times. Okay, we're going to thank Sam again. Thanks everyone for coming.